Hello, this is Gregory Maxwell, and this lesson will be about inverse functions. Inverse functions. Now, in order to do this, you should have reviewed basic functions, basic properties of functions, as well as composite functions, which you can find some of those lessons on this channel, as I've covered already. Now, let's get into it. A quick note here, many of the slides, most of the slides in this PowerPoint in this presentation will be from Shauna Hader, who created a series of PowerPoint presentations on inverse functions. Now, let's start off with a bit of information here. If we recall, when we're talking about functions, it's a rule that matches each x value in the domain to exactly one y value in the range. So in this case, for example, 1 matches to 6, 2 matches to 2, 3 matches to 4, 4 maps to 8, and 5 maps to 10. So what we have here is a function. Now, the inverse of a function takes the y values back to their originating x values. So in this case, the 6 will go back to the 1, the 2 will go back to the 2, the 4 goes back to the 3, the 8 goes back to the 4, and the 10 goes back to the 5. If the inverse of the function is also a function, then we call it the inverse function. And we use the word the because that's the only function that will work that way. If you have a function whose inverse is also a function, that inverse is a unique inverse. That means it's the only one that works that way. So that brings us to how we can tell if the inverse of a function is also a function. If you notice here, I have a different example, and in this example, we have 1 mapping to 4, 2 to 2, 3 to 6, 4 to 8, and 5 also maps to 6. So we have two numbers that map to the same y value, two x values that map to the same y values. If I do the inverse of that mapping, the 2 will go back to the 2, the 4 will go back to the 1, the 6 will go back to the 3, but will also have to go back to the 5, and the 8 will go back to the 4. So as you see, this inverse is not a function. Even though the original mapping was a function, the inverse of that function is not a function. So not all functions have inverses that are functions. Not all functions have inverses that are functions. There are certain types of functions that have inverses that are also functions, or we can say have inverse functions, namely one-to-one function. A one-to-one function is a function that matches one x value to one y value, and each y value must come from only one x value. So in other words, another way of saying it is, if I have two x values that map to the same y value, then those two x values must have been the same thing. Or if I have two different x values, they will have to match to two different y values. They cannot match to the same y value. So for a one-to-one function, each x value must match to a different y value from every other x value. So let's take a look at this example here. This is a function. However, it's not a one-to-one function because all the x values are mapping to the same y value. So the inverse of this function is not a function. It does not have an inverse function. If the inverse is not a function, we say that this function is not invertible. When we say a function is invertible, we mean that its inverse is also a function. So when we find the inverse of the function, the inverse is also a function. Here's another example. 1 maps to 6, 2 maps to 4, 3 maps to 2, 4 maps to 10, and 5 maps to 8. That's a one-to-one function, so it is invertible. That is, its inverse is also a function. Now, recall that we use the vertical line test to determine if a graph is a function, if a relation is a function. Now, there's another test to test if a function is invertible, if it's one-to-one. We start out with a function, and then we use what we call the horizontal line test. Now, remember, we only need to use the horizontal line test if we already know that the graph is a function. If the graph is not a function, it can't be a one-to-one function because it has to be a function to be a one-to-one function. This graph here that we have, the graph of x cubed, Every time I draw a vertical line through the graph, it crosses it on exactly once, no more than once. So this is a function. This circle, which is not doesn't look quite like a circle because the scales of the x and y axes are different. It is not a function because it fails the vertical line test. And this absolute value graph is a function because it does pass the vertical line test. So the first graph and the last graph are functions. Now the question we want to determine is are these one-to-one functions. Now look at this graph of x squared. This graph is a function clearly, but it doesn't, if you draw a horizontal line through the graph, it cuts it more than once. That means there's a y value that corresponds to more than one x value. This is a function, but it is not a one-to-one function. So this function is not invertible. Its inverse is not a function. On the other hand, the x cubed graph that we just saw, it's a function, but wherever I draw a horizontal line anywhere, the graph will cross it exactly at no more than once. So this is a one-to-one function. So this function is invertible. So its inverse is a function. So if the horizontal line crosses the graph more than once, then the graph is not one-to-one. It's not invertible. Of course, again, we need to make sure that the graph is a function to begin with. So this graph is a graph of 1 over x, the reciprocal function. Wherever I draw a horizontal line, the graph will cross it at most once. There is a horizontal line that does not cross the graph at all. That graph is, of course, that is the line y equal x. The x-axis y equals 0, but that's fine. That is still fine. It is a one-to-one function, so the function is invertible. This graph here is a graph of a circle, which is not a function. So it cannot be a one-to-one function because it's not a function. It still fails the horizontal line test, but even if it did pass the horizontal line test, it would have failed the vertical line test. So we're not dealing with a function here. So we're not dealing with a one-to-one function. This graph is a function, it's the absolute value graph, but when I draw a horizontal line through it at least once, the horizontal line cuts it more than one time. So this is not a one-to-one function, so this function is not invertible. The function is not invertible. Now let's take a look at the graph that we just saw, the graph of x cubed. The graph of x cubed. X cubed is an invertible function. The graph we know, when we plug in -2, we get -8. When we plug in -1, we get -1. When we plug in 0, we get 0. When we plug in 1, we get 1. And when we plug in 2, we get 8. So we can plot the points and draw it with a smooth curve, and that's a one-to-one function. Now, if I want to find the yes, it is. And the inverse, if I want to find the inverse, all I do is the inverse operation. The inverse operation for x cubed is to do the cube root. That's what undoes the cube. So the cube root will give us back the original. So now what will happen is this function will be the reverse operation. It undoes what f of x is. It's called an inverse function. The symbol we use for the inverse is we use a subscript of -1. We're saying f to the -1, so to speak. That's what it looks like. It's not really f to the -1. We're saying undo f. So this is f inverse of x. Now, very important here. F inverse of x does not mean multiply by x. It means you're undoing it. And therefore, your input for your inverse function needs to have been the output for the original function. So your y values for f are now going to be your input values, your x values for f inverse. Your outputs become your inputs so that your inputs become your outputs. So when you're doing the inverse of a function, basically you're just switching your x and y values. So my new x values are -8, -1, 0, 1, and 8, and my new y values are -2, -1, 0, 1, and 2. When I plot those points, there we have the graph. And the graph actually, they look like they have some type of symmetry. The graph of one function looks like it's symmetric with the graph of another function, but the symmetry line is not the standard axis. The symmetry line is actually the line y equal to x. In other words, if you draw the inverse of a function on the same graph grid as you draw the function, one will be a reflection of the other one about the line y equal to x. And basically what's going on is you're switching x and y. The xy becomes yx. What is the x value for one function becomes the y value for the corresponding inverse function. So geometrically, if a function and its inverse are graphed, they are reflections about the line y equal x, because the x and y values have changed traded places. So the domain of a function will now become the range of its inverse, and the range of a function will now become the domain of its inverse. So if we start out with an x as an input to one function, that will become the result in the inverse. So if you get two functions, then they undo each other. The inverse of a function undoes the function. So if you do a composition of one function with its inverse, you get x. All right, so f of g of x is x, and g of f of x is x. That will indicate that f and g are inverse of functions of each other. These functions are inverses of each other. Let's take a quick example here. We have the graph of f of x equal to x minus 2 squared. Now, if I draw the graph f of x equal to x minus 2 squared, we have a parabola that's shifted to the right 2 places. That is not a one-to-one function. However, if I restrict the domain to only be values of x greater than or equal to 2, that means starting from here, where it touches the x-axis and moving to the right, then I will just ignore the left side. The left side will disappear, and all I have is just that right side there. Now that is a one-to-one function because I have restricted the domain. And so its inverse will be a one-to-one function. And the inverse of this function is g of x equal to square root of x plus 2. In a moment, we will learn how to find the inverse. But for now, let's check to see if they are legitimately inverses. When I compose f of g, the result is x. So when I do g and then do f, they undo each other, we get back the original. Likewise, if I do g of f, they undo each other and they get back the original. So f and g are inverses of each other because they undo each other. So the question then is how? How do we find the inverse of a function? That is a relatively simple process. There are 4 simple steps. One of them is a cosmetic step, and the other one is functional. The other two of them are functional, but the key step I will indicate in a minute. The first step, which is the cosmetic step, is to just replace our f of x or g of x or m of x or whatever the name of the function is with y, because f of x represents the y value, the output of the function. Once I do that substitution, then I am going to do the key step. This is the most important step of all, which is interchange x and y, trade places with x and y. That means your y values become x and your x values become y. Then you now have the inverse of the original function, but it may not look like a function. So what you do is you solve for the new y. Once you've changed x and y, then you solve for the new y, and that new y is the output for your inverse function. So now that you will change the name back to the inverse of the original name. So if the original function was f of x, then the new guy is f inverse of x, f with that -1 superscript. Let's do a quick example. We have the function f of x equal to 4 over 2 minus x. 4 over 2 minus x. Step 1, we will replace all our f of x's with y. That's a cosmetic step. We still have the same function. Step 2, which is the most important step, we will trade places between x and y. So where we see y, we will put x, and where we see x, we will put y. So now we have x is equal to 4 over 2 minus y. This is now the inverse function for the original function, but it doesn't look like a function because the y is not by itself. So the next step is to isolate the y. So we're going to solve for y. What we will do is multiply both sides by 2 minus y. Then we'll distribute the x to both parentheses. Then I'll solve for y. Subtract 2x from both sides and then divide by -x. So this now is my inverse function. This y value was originally the x value in the original function. So now we're dealing with the inverse. Since it's the inverse of the function, we will call it that. So now f inverse of x is 4 minus 2x over negative x, or we will put the negative in front. We have the negative of 4 minus 2x over x, or if you multiply the top by -1, we get 2x minus 4 over x. That is the inverse. Either one of these is the inverse of the original function. How do we know if we are right? Let's do the composition. We'll just do the composition in one direction to check. F of f inverse of x. We substitute f inverse of x into f of x. So wherever I see x, I will put what f inverse of x stands for, and then I simplify. I combine the like terms in the denominator. I combine the denominator into one fraction. 2x minus 2x is 0, and then you have 4 over x. And then when you multiply top and bottom by x, you'll get x. So this function is the inverse of the original function, because when you do the composition of one with the other, you get x. And that is our instruction. Now let's do some examples. We are going to find the inverse of each of these functions, and then we will check to see if they are, we're going to check to see if they are, if our inverses are correct. So let's start off with the first one. This is a non-horizontal straight line, so we know this is a one-to-one function. So let's start off with this one here. So for step number 1, I will replace my f of x with y. That's just a cosmetic step. Step number 2, interchange x and y. That is the most important step. Step number 3, solve for y. Add 1 to both sides and then divide by 3. So we get x plus 1 over 3, or we can write it as 1/3 x plus 1/3. So then the last step is to call f inverse of x that function. So we're going to call f inverse of x 1/3 x plus 1/3. That is the inverse of the function. Very simple. 4 steps. Write y in place of the name of the function. Switch x and y, solve for y, rename the function with the y f inverse of x. Now let's verify that this is the inverse of the function. We're going to do f of f inverse of x first. So we're going to substitute f inverse of x into f of x. So that is 3 times 1/3 x plus 1/3 and then minus 1. When I distribute the 3, I get 1/3 x times 3 is x, 1/3 times 3 is 1, and then the minus 1, which gives you x. So that works. Now let's do the other direction. F inverse of f of x. So now I'm going to do 1/3 times 3x minus 1, then plus 1/3. When I distribute the 1/3, I get 1/3 times 3x is x, 1/3 times -1 is -1/3, and then plus the 1/3, and that gives me x. So there we have it. We see then that in both cases, when you do the composition of one function with the other function, the result is x. So the functions are inverses of each other. Now let's go with the next example. First, we replace f of x with y. That's a cosmetic step. Then the key step, the most important step, switch x with y. Wherever we see y, we put x. Wherever we see x, we put y. Then we solve for y. And that gives me y is equal to the cube root, because I have to take the cube root of both sides to get the y by itself, of x minus 2. And then finally, to name my function, f inverse of x is equal to the cube root of x minus 2. 3 is a little big, so let's make it a little smaller. Now, to check if we are correct, we'll do f of f inverse of x. F of f inverse of x. So that will be cube root of x minus 2, that's raised to the power 3, and then plus 2. Now the cube root is undone by the cube. So that leaves just the radicand, x minus 2 plus 2, and the negative 2 and the 2 will cancel each other, just leaving the x. So as you can see, one composition works out to be correct, and then f inverse of f of x should also work. What I will do is replace all my x's in f inverse of x with what it stands for. So it's the cube root of x cubed plus 2 and then minus 2. And that, of course, gives you the cube root of x cubed. And then that gives you x. And that was because the 2's would have cancelled and the cube would have cancelled the cube root afterwards. So both functions, both compositions give you x. Next up, for this function, again, we replace f of x with y, and then we do the key step, which is interchange x and y, change places, and then we solve. We're going to do the cube root of both sides, and then I'm going to solve for y. Cube root of x, then plus 1. So then my function is f inverse of x is equal to the cube root of x plus 1. So to check if we have the right inverses, I'm going to do f of f inverse of x. So that gives me, open parentheses, cube root of x plus 1. That's my f inverse, then minus 1 because that's what f says, then cube the result. Well, the 1 minus the 1 is 0. So now we have the cube of x cubed, of the cube root of x, sorry. And that simply gives us x because the cube undoes the cube root. So that's what we want. Check. Then let's go on to f inverse of f of x. So now we take f inverse, which is the cube root of quantity x minus 1 cubed, and then outside of that we put plus 1. So the cube root undoes the cube, and that leaves us with x minus 1, then plus 1, which gives us x. Now for number 22, part A, we're going to, of course, replace f of x with y. Then we're going to interchange. We're going to trade places between y and x. So we have x is equal to 2 over y. Then we're going to solve for y. I'm going to do so by multiplying both sides by y and then dividing both sides by x. So y is equal to 2 over x. And that means f inverse of x is the same function as f of x. F and f inverse are the same function. F is its own inverse. It undoes itself. So when we're doing the composition, whether we're doing f inverse of f of x or f of f inverse of x, we're doing the same thing. We're basically doing 2 over 2 over x, which is 2 times x over 2, which is just x. And that shows that the function is its own inverse. Now, of course, I strongly recommend that you do a lot of these questions on your own and check them out to see what you can do here. Let's do a few more examples here. These examples are a little bit more involved, but again, I strongly recommend that you do these questions on your own and then check the work. Step number 1, we're gonna replace f of x with y. So we have y equal to 4 over x plus 9. That's just the 1 over x graph stretched by a factor of 4 and shifted shifted upwards, sorry, by 9. So it's still a one-to-one function. Then the key step, x is replaced by y and y is replaced by x. So we have x equal to 4 over y plus 9. Then we solve for y. I'm going to subtract 9 from both sides. Then I'm going to multiply both sides by y. Then I'm going to divide both sides by x minus 9. There we have it. So then f inverse of x is equal to 4 over x minus 9. Now, let's take a look at what that means. This is just a graph shifted to the of 1 over x shifted to the left, to the right 9 units after being multiplied by 4. Now, if we're correct, then f of f inverse of x should be x. So we do 4 over x minus 9 and then plus 9. So basically that's 4 over 1 times x minus 9 over 4. And then plus 9 to the result. The 4's cancel, and we end up with x minus 9 plus 9, which gives us x. So this one checks out. Now let's do the other inverse, the other composition, f inverse of f of x. So now I take the inverse function, 4 over x minus 9. I'm going to substitute the original function into that, 4 over x plus 9, and then minus 9 from the inverse function. Clearly, the 9's cancel each other out. And then we have 4 over 1 divided by 4 over x, which is 4 over 1 times x over 4, which of course gives you x. So this function does check out. Now this one looks a little bit challenging. It only looks intimidating, but we can approach it the same way, systematically. So we replace f of x with y. That's the cosmetic step. And then we are going to interchange x and y, trade places. X is equal to 2y plus 3 over y plus 1. Then we need to get the y's into 1y to become 1y. So what I'm going to do is I'm going to multiply both sides by the denominator here, kind of like cross multiplying. So we have x times y plus 1 is equal to 2y plus 3. Then I am going to distribute the x, and the reason is so that I can free up the y that's inside the parentheses so I can join it with the other y on the other side. So what I will do now is I'm going to subtract x from both sides, and at the same time I'm going to subtract 2y from both sides. And what that will do is have me with xy minus 2y on the left side and 3 minus x on the right side. And then what I will do is I will factor out y. That leaves me with x minus 2 on the left. And on the right hand side, I just have 3 minus x. Then when I divide both sides by x minus 2, I get y equal to 3 minus x over x minus 2. So that means that f inverse of x is 3 minus x over x minus 2. I just noticed that I made an error here, so let me correct that right away. That was supposed to be a minus, which means this was supposed to be a minus, which means this was supposed to be a minus, which means this is supposed to be x minus negative x minus 3. And then that means my result is now going to be negative x minus 3, which can be written as, if I multiply the numerator and denominator by -1, I have x plus 3 over 2 minus x. Either one would be fine. Now let's check to see if our inverse is correct. So f of f inverse of x, this is supposed to be f inverse, is equal to, now this will become a little tedious, 2 multiplied by the quantity, let's use the second one, x plus 3 over 2 minus x, then minus 3 over x plus 3 over 2 minus x plus 1. Now to simplify that, all I'll have to do is multiply the numerator and the denominator by the common denominator, namely 2 minus x. Once I do that, I distribute it to the numerator, and then I end up with 2 times x plus 3, then minus 3 times 2 minus x. And then the denominator is x plus 3 plus 2 times, plus 1 times 2 minus x. Simplifying, we end up with 6. We end up with 6x plus 6 minus 6 plus 3x. And I'm in a little area that's 2x plus 6 minus 6 plus 3x. And in the denominator, we have x plus 3 plus 2 minus x. Two x plus 3x is 5x. And of course, 6 minus 6 is 0. 3 plus 2 is 5. And x minus x is 0. So we end up with x. Because of space, I won't do f inverse of f of x, but it's done similarly. So I will encourage you to check that one on your own. So our function is correct. So now let's do a last few examples here. In this case, we're simply going to graph the inverse of the function. Now it's a very simple process. This is very easy. What you do is you identify key points on the graph, and then you just reverse the x and y coordinates. So in this case, I've already identified the key points in the graph: 0, -4, 2, 0, 3, 2, and 4, 4. So for the inverse, to get the inverse of those functions, I'm going to write the inverse in red here. I'm going to just switch the x and the y. So now this becomes -4, 0. This becomes 0, 2. This becomes 2, 3. And of course, switching 4, 4 will still give you 4, 4. And now I'll plot the points. This is -4, 0 is this point right there. 0, 2 is that point right there. 2, 3 is this point right there. And 4, 4 is that point right there. And so now my graph is simply the straight line going through those points. Let me make a little adjustment to my graph here to make sure it's more aligned. But you get the idea. There you have it. This red graph here is the inverse of the indicated function. This is the inverse. Next up, with this one, we have 3 points that are marked here that we use. So let's see, -3, 0, that's this point here, that becomes 0, -3. -1, 2, that becomes 2, -1. And 5, 3, that becomes 3, 5. And then we just plot our points. So 0, -3, 2, -1, and 3, 5. And now we join them. Since those are straight line segments, we'll do that again. So these 2 points are connected here. Those points are connected there. Oh, I neglected to add my little arrow. So let's add a little arrow to that. And there we have it. That is a graph of the inverse of the function. Last example, this is a curve, so it may be a little bit more tricky. 0, 1 becomes 1, 0. That's the matches to 1, 0. 1, 2 matches to 2, 1. And 2, 4 matches to 4, 2. So let's plot those points. 1, 0. 2, 1. And 4, 2. As you can see, the graph kind of levels off along the x-axis, so we're going to have it level off along the y-axis here. And that's kind of a rough sketch of what's going on here. Again, it's the inverse of the function. It's like they're mirrored in the line y = x. So this is the inverse of our function. Now, this concept is key for later topics such as logarithms and exponential functions, rational functions as well. So you might want to make sure you get a lot of good practice with this topic. This is a very, very important topic. As always, I strongly recommend that you do your Khan Academy. Check out exercise on Khan Academy, as well as openstax.org, openstax.org. That's a free open source textbooks. They have college algebra textbooks as well as other courses, both math and non-math subjects, as well as, of course, they have an app, an Android app. I'm not sure if it is also available for iPhone. Free app, OpenStax. And as well, please practice, review the videos on Khan Academy. They are really excellent videos on Khan Academy that may even explain it even clearer to you than I have here. And also practice the Khan Academy exercises that are related. That's all for this lesson. All the best. Keep working.